Be talking about the upstream and downstream effects of the SVC. So the environmental controls that are driving the SVC, and then the downstream effects that actually it causes on the parent supercell. If you've seen AnyMed presentations, you've probably seen this time lapse. It's pretty quintessential for what I'm trying to show here. This is back in May 27th, 2019 in Imperial, Nebraska. And we have a sculpted mothership supercell once it restarts. The mid-level mesocyclones up here, but we get this tail cloud kind of feeding into the low levels. And if you follow the little individual cloud traces, you can see that not only is it moving into the updraft, but it's also kind of rotating around almost an invisible spine in the center of that cloud feature. And that is a physical manifestation of condensation caused by the pressure perturbation within the SVC itself due to the vorticity magnitude there. So I'll be focusing on the dynamics of that primarily through this talk. So for some acknowledgements, I want to thank Dr. Chris Weiss for being my advisor, taking me through all those years, being an inspiration. You know, he did start as a grad student a long, long time ago. And as he progressed in his career, he did a lot of really critical thinking and pondering and contemplation on how to best guide his students into the successful career that he has followed. And then he had a realization, and he was like, of course, I just need to follow the roadmap that describes the way to do this. And so after explaining this to me and showing me the path on guiding me into this direction, I really grabbed the reins and found my steed and was able to finally make it here for today for my PhD defense. So for that, I appreciate. Finally, I'd also like to thank the Tweesters group and alum. I've spanned many years, and so I've seen a lot of people come and go, and you all have been super great and helpful. Plus the fieldwork adoptees in the radars and the sticknet trucks, wherever that we cross paths, you really kind of helped us keep stay sane and kept it lighthearted. So we have got many great memories there. For my dissertation committee, thank you, Johannes and Eric, for being on my committee. Johannes, this work is kind of right down your path. So hopefully you should enjoy it. Now, Eric, this is a little bit outside of your wheelhouse, but who's to say that lightning has nothing to do with SVCs here? So this is one of our SVCs that we captured in 2018. It's invisible. There's no condensation there, but the lightning is actually illuminating a little bit of the density current dynamics down here. So you could actually see visibly the SVC with the lightning. Some hope. It does. Also, I'd like to extend thanks to my friends and family for keeping me accountable all these years to, finish. And then my extremely patient and loving wife and daughter for sticking with it and kind of keeping me accountable and helping me stay sane through all the years and efforts. So I appreciate that. So let's kind of jump right into it. I got a lot to cover, like Chris said, and not a lot of time. So the SVC was originally discovered back in 2017 by Lee Orff and collaborators in their very high resolution EF5 tornado simulation. He described it as just a coherent tube of streamwise vorticity that is flowing into the low level updraft, tilting upwards and kind of wrapping around their EF5 tornado. And so this seemed to be a pretty causal relationship because he noticed that the genesis and strength of the SVC correlated with the EF5 genesis as well. And as the SVC dissipated, so did the tornado. There's also not only a coherent region of streamwise vorticity lifting up, but there's also this vertical vorticity sheet on the leading edge of the forward flank boundary and SVC. And it was these parade of vortices that actually kind of came together and formed their EF5 tornado. My master's work focused on this with, albeit quite less resolution in a CM1 simulation. And I found that the primary rotor, the primary streamwise vorticity was located on the center of a steady state Kelvin-Helmholtz billow in both time and space. And it was a very coherent rotor through the entire thing. that extended for more than 10 kilometers and then lifted up into the updraft. I also found that horizontal stretching, 3D stretching and tilting really contributed a lot to that vorticity tendency, that vorticity magnitude as a total in the SVC. Baroclinic tendency was pretty small comparatively. There was still some on the leading edge of the boundary, but for integrated values, that wasn't a huge impact. Merdzik et al. 2020 verified the SVC's existence in real life using 4 Vortex-2 supercells, dual Doppler analysis. And this is kind of shown down here where there is a coherent region of streamwise vorticity. And in a vertical cross-section, it kind of looked like a Kelvin-Helmholtz billow there as well. In my study, I also found that there was a coherent forward flank boundary in a couple different supercells, and there was a Kelvin-Helmholtz billow associated with that in the vertical cross sections, and a fair amount of vorticity that we'd expect as well, that correspond to our simulations really well. Finally, Hozik et al. 2023 identified a transient SVC in a multi-Doppler analysis of a weakly trinitic supercell. So mine was non-trinitic. Merdzik had a couple weakly trinitic and non-trinitic, and Hozik has a weakly trinitic. And so the correlation between trinados and SVCs is still a little poorly understood. Moving forward in time, Abby, previous alum from this group, used an ensemble approach that looked at the streamwise vorticity magnitude and found that there is very little sensitivity to the magnitude itself within the SVC to the tornado. However, the position was important, and she found that if the SVC was located more east and southerly, that favored stronger tornadoes. Whereas if it was higher in the higher depth, that actually favored weaker tornadoes, where if it was lower to the ground for a longer period of time, it actually favored stronger tornadoes because it tilts up more drastically. Gray and Frame also looked at SVCs and some upper level veering and backing in their photographs, which we'll talk about in a bit. And they found that the SVC was correlated, did not find that the depth of the SVC was correlated with mesocyclone strength, which was kind of opposite of Abby. And they also found that orientation was, but it was in the opposite direction of Abby too. So there's a lot of kind of uncertainty as to what's actually going on here. And they also found that baroclinic tendency was much smaller than stretching. And 89% of their TLVs, tornado-like vortices, in their simulations occurred within about 1 kilometer of the tilting SVC. So that seems like there might be a causal relationship there. Moving on to low-level updrafts, Finley et al. 2023 showed that the low-level mesocyclone almost in its entirety was driven by the SVC in their simulation. The gray is their streamwise vorticity, and as that lifts at about 1 kilometer, we see a maximum in low-level updraft and mesocyclone strength. So it's pretty circular, pretty columnar. Kofer et al. 2023 looked at a variety of different simulations, and a lot of the low-level updrafts appeared to be the shape of a comma. And the comma head was larger and stronger for trinitic supercells, where kind of like here or here, whereas with the non-trinitic supercells, the comma shield was the larger part of the low-level updraft, and that's where the maximum vertical velocities were located at. So kind of looking at some of our Ka observations, we really have spread the gamut on a lot of our observations. We have a trinitic SVC, which was grading New Mexico, and note that this Kelvin-Helmholtz billow with strong vorticity and stuff extends all the way up above 2 kilometers, which is incredibly deep compared to a lot of the previous simulations as well as observations. We have a non-trinitic SVC that I just talked about. We have a trinitic non-SVC in Morton, where we actually had 2 tornadoes, but the forward flank at this time was really relatively small, negligible kinematic signal. There was an SVC later in that storm, though. And then finally, in 2019, we had a non-trinitic non-SVC with a mature supercell and a kinematic boundary, but there's no coherent vorticity with that. So I kind of want to look at 2 things. I want to look at the upstream effects of the environment on the SVC. And I have three main hypotheses with this. That larger storm relative inflow flowing into the storm will increase the likelihood and strength of the SVC. And this is through the physical pathway that storm relative inflow modifies the updraft, makes it stronger and wider. And what goes up must come down. The mass flux is larger in the larger updrafts. The mass flux down is larger in stronger downdrafts. That leads to stronger cold pools and stronger and larger baroclinic zones that we have these SVCs occurring. It also will have a stronger inflow low based on that updraft width. And there's a stronger and larger breadth of horizontal accelerations around that inflow low that could modify the SVC. We also have going to change the mid to upper level backing versus veering of winds if we're rotating those clockwise or counterclockwise. So if we rotate the upper level winds counterclockwise, that will negatively impact SVC formation. So the idea there is that the precipitation and boundaries will be displaced away from the inflow low. And that horizontal accelerations around the inflow low will not be able to tap into that baroclinic zone, and so an SVC will not form. The vorticity will also have a larger crosswise component to where that boundary is oriented. And then finally, we have strong low-level shear in the lowest 1 kilometer. That will support SVC existence and strength the most. And SVCs will not exist with weak low-level shear. A stronger mesocyclone, so stronger low-level shear makes a stronger mesocyclone, which leads to a stronger inflow low as well. And so you're going to have greater horizontal accelerations, as well as having more ambient low-level shear, ambient streamwise vorticity to amplify and build upon. And then finally, for the downstream impacts, we're going to see the SVC, and it's clear that the SVC is not necessarily a smoking gun for the TLVs, but I propose that TLV genesis and maintenance is better with an SVC present than without one. I'm going to look at environmental parcels, and I hypothesize that environmental parcels will supply the front shield of that low-level updraft, whereas with the SVC parcels, if it's present, will supply the comma head part of the low-level updraft, where some of the strongest vertical velocities are, that is also located directly over the tornado. And then finally, the nonlinear dynamic vertical accelerations associated with the vorticity within the SVC as it tilts up, that vertical acceleration will favor tornado genesis by stretching any pre-existing vortex patches that may be present around that area. So I'm not going to dive into a whole lot of methods. I don't have a whole lot of time. The thermodynamic profile is based on the Wiseman-Klemp 1982 sounding that was modified to emulate the Caniglio-Parker 2020 EF1 composite based on field observations around supercells in the last couple decades. I decreased the warm nose just a little bit and moistened the boundary layer to support stronger maintenance of supercells. I also developed my own kind of analytic hodograph design based on Archimedean spirals that kind of take the shape of actual hodographs that we observe in nature. And there is some precedent for that given the Ekman spiral. I'm going to put this up there in case you're interested and want to look at it later, but I don't have time to go through it all now. But basically, I calculate the arc length around the Archimedean spiral and apply that to a shear profile that I can construct using any sorts of functions. Here I use a 3-piece function with a decaying exponential, a logistic curve, and a skewed normal distribution PDF to get kind of this blue line here. And overall, this matches the vertical shear profile of the Caniglio-Parker composite hodograph pretty well. And when we apply that shear profile to the Archimedean spiral hodograph, we get a hodograph that looks pretty similar to what their composite hodograph looks like. And so we can use this method to construct the hodographs that we want to use for this study. So like where our hypothesis stated, we have 3 primary things that we're looking at. We're looking at the storm relative inflow strength. We're looking at the angle, the upper level backing versus veering winds, and we're looking at the low level shear magnitude. And so I was able to adjust for all of these relatively independently and tune them so we can get exactly the storm relative inflow desired based on the bunker's motion. And we were we're reframing the upper level backing versus veering as the inflow outflow angle, which was talked about in Kirkpatrick and McCall in 2002, I believe. And that's basically the angle between the 0 to 1 storm relative wind, the storm motion, and the 9 to 11 kilometer mean storm relative wind. And so if you think about it here in this orange, if we take the mean 0 to 1, go to the storm motion and go out here, that angle that makes is approximately 150 degrees for the orange. It's 180 degrees for the green and 120 degrees for the blue. And so the upper level backing will be in blue, the upper level veering will be green in this case, but that will be a higher inflow outflow angle. There are 27 total experiments here, only 22 were viable, and so we're going to be analyzing those more in depth. I use CM1, horizontal grid spacing, 125, Morrison double moment microphysics scheme. I have a free slit bottom boundary condition, which could cause some problems, but also there's a lot of precedent for that. And so I wanted to stick with what is kind of known for that. And then I developed my own Kalman filter storm centering algorithm. Unfortunately, I'm not able to talk about it today, but hopefully there will be a paper out soon about that. So experimental overview. So this is all of my TLVs that I identified in every single experiment as a time series. So red are cyclonic TLVs, blue are anticyclonic TLVs, and the green boxes are where SVCs are present. And in the bottom here, I have the SVC magnitude with time as well. If you notice, some of these SVCs are over 2 hours long in some simulations, whereas in other simulations, they're relatively short. And by relatively short, they're still 30 minutes long, which is pretty impressive. So they're not transient features created by quick surges or whatever else. They're steady state features that are present for a long period of time. So we have 3 hours of analysis time in every simulation. So between hours 1 and 4 is where I focused on. And we have 22 total simulations. So that leads to a sample size of about 4,000 individual times. We're going to treat each time as independent. Now, obviously, that's not the case. One time is going to be dependent on the previous time and the next time. However, and so that will break some statistical assumptions. However, this will also increase the sample size significantly for some of the statistical uses as well. And what we can do there is at each time recalculate what the vertical wind profile away from the storm looks like. And so the storm relative inflow, the inflow outflow angle, the low level shear magnitude is going to change throughout the simulation at each time. So we can compare that instantaneous change to what is observed in the supercell. The markers are a little hard to see, but basically blue here means that we have inflow outflow angles weak, low. So that means upper level backing versus red is upper level veering. And this will be a plot that you see a lot of here coming shortly. So just kind of get an idea and feel for this. The statistics are in the top here with R squared value on the very top, Pearson and then Spearman correlation coefficients with a linear regression line as the red line situated here. These are all 3 independent variables that we wanted to look at, and we wanted to show that they are truly independent. So the B and C are very independent. The R squared value is less than 1% variance of one variable explaining the other variable. The first one, there's about 9.7% of the variance of inflow outflow angle explained by storm relative inflow, but we're still going to assume that they're relatively independent there. So applying those statistics, we get the covariance matrix of doom. And so we can apply that R squared value to the green in the bottom left, relating each supercell metric to each other supercell metric. And on the top right, we have our Spearman correlation coefficient with the hatching indicating a significant p-value. If we walk through this, we have our 3 independent variables that we're comparing to everything else. Our updraft metrics, such as updraft mass flux, width, and vertical velocity, our downdraft metrics, our mesocyclone metrics, such as updraft helicity and rotational velocity. We have our cold pool metrics, our inflow low metrics, our boundary, so forward flank reflectivity gradient, forward flank convergence boundary, and left flank convergence boundary, as well as the winds associated with them. SVC metrics, and then finally TLV metrics. So we're trying to investigate those pathways that I had talked about earlier and see walking down the pathways, what are the correlations there? Now it's really kind of tough to go through that just with this. So we're going to walk through each one of those pathways with the scatter plots. So with the storm relative inflow, we predict that is going to affect the updraft width. And we see that updraft radius and mass flux are increased with storm relative inflow. That's a check mark. But effective radius is actually highly correlated with mass flux. So that's the true connection there. It just happens that the storm relative inflow is modifying both the radius and the mass flux there. If we look at downdraft volume, we also see that storm relative inflow is driving a larger downdraft volume and a larger downdraft mass flux, as well as a minimum vertical velocity within the downdraft there. And if we compare the updraft metrics to that, the correlations are actually better than the storm relative inflow. So again, that connection between the updraft and the downdraft makes sense. Moving forward to the cold pool. So we have a rainfall footprint. So precipitation footprint of the forward flank, rear flank, all that combined is highly correlated with the storm relative inflow. And so we're going to have larger footprints of precipitation with larger storm relative inflow. We have more ventilation overall. Our cold pool gets colder with larger storm relative inflow. We have more mass flux, stronger cold pool. And our cold pool depth has actually increased with storm relative inflow as well, which is a common metric used to kind of decide the strength of cold pools. If we look at the downdraft mass flux, the relationships get stronger as we would expect because the downdraft is driving that cold pool. And if we compare the cold pool values to each other, for instance, minimum theta rho versus rainfall area, that shows a negative correlation. So our warmer cold pools are associated with smaller rainfall areas. Again, makes sense. So if we look at composites of the storm relative inflow, for all of the inflow outflow angles, all of the low level shear values, for a storm relative inflow of 15.5, 18, and 20.5, we can kind of get an idea of what that actual variable is causing. So we see with increasing storm relative inflow, we have a larger footprint of outflow surges, defined by the grain frame 2021 indication there. We also have a larger number of outflow surges, as we would expect, with a larger area as well. And the orientation has actually moved north relative to the updraft, which is in the crosshairs there. And the rotation is actually shifted a little bit to the right and clockwise. So that's a little bit interesting. If we look at small raindrop number concentration, which has been known to drive cold pool magnitude by evaporation. So if we're looking at 1 millimeter raindrop concentrations alone, we can see that the maximum concentration of the small raindrops occur with the largest storm relative inflow. And with the weak storm relative inflow, it's obviously the lowest number of small raindrops. And that centroid also increases distance away from the updraft with stronger storm relative inflow due to ventilation there. And then our cold pool follows that path pretty well, where our cold pools are stronger with stronger storm relative inflow because of those smaller raindrops. So if we kind of step back then and look at the inflow low relative to the storm relative inflow, we also see that the inflow low magnitude decreases or gets stronger because it's a negative pressure perturbation, gets stronger with the stronger storm relative inflow. And the distance actually gets farther away from the updraft with stronger storm relative inflow as well. And that makes sense because it's the linear dynamic pressure perturbation from the updraft that is driving that inflow low position and strength as well. The orientation is relatively minimal impact with that. But if we compare the updraft mass flux to the inflow low instead of the storm relative inflow, we see a lot higher correlation. So again, the updraft is driving that inflow low. So let's bring this all back to the SVCs. That's what we care about, right? So storm relative inflow should affect SVCs, right? Not quite. The magnitude of the SVC does not seem to be correlated with the storm relative inflow. And actually, if we look at these little kind of groupings right here, right here, right here, that's all from one single experiment. And we see that it is spanning different storm relative inflows, but the SVC magnitude is not appreciably changing at all. And so that's pretty independent. There's no correlation there. Orientation also shows very minimal effects. However, the presence of an SVC, so if we take the population of SVCs occurring in all the simulations and the storm relative inflows of those versus the null cases of no SVC, we can see that those SVCs are much more likely to be present with stronger storm relative inflows than with not. For TLVs, there's really no correlation. There might be a small statistical signal in the presence of TLVs with stronger storm relative inflows in this bottom right here. But that's a kind of a hotly contested thing in the literature right now, and I'm not going to go into that with this data set. If we look at inflow-outflow angles compared to cold pools, so we should be changing that precipitation orientation relative to the updraft. But we also see that was not expected, a change in the footprint of the precipitation based on the inflow-outflow angle. So in the blue, again, we have upper level backing here, low inflow-outflow angles. We are actually increasing the precipitation footprint with those low inflow-outflow angles, whereas if we are veering, and so we're going to have more precipitation more in the inflow technically. That footprint is actually smaller, which is relatively interesting. And the cold pools are weakly associated with that. Theta rho is weakly associated. But the R squared is a 0.05. So 5% variance is not a great signal there. Maybe. All right. So kind of going back and then going to this figure again, we have outflow surges in the top there. We have more outflow surges over a larger area in upper level backing environments. And that's really kind of a meridional stretch of those outflow surge locations. And if you're familiar with like the left flank versus forward flank kind of identification there, the outflow surges are predominantly in the left flank of all of these supercells, but that forward flank is almost merging with the left flank in that composite reflectivity graph there, shown as well in the upper level backing. And so we're getting some weird kind of upper level size sorting issues that may be influencing where these outflow surges are occurring. There really is no solid signal in the centroid position or orientation with that. If we look at small raindrop number concentration, we see that there's a lot more small raindrops with our upper level backing really close to the updraft, which is in this plot right here. And the concentrations are much larger. And as we increase in inflow-outflow angles, that centroid gets a little bit further from the updraft, and there's smaller small raindrop concentrations total. And then if we look at cold pools, again, the same signal can be seen as we saw with the raindrops. We have colder cold pools in upper level backing experiments, and upper level veering, we actually have a little bit warmer cold pools, and that cold pool centroid or minimum rather is farther away from the updraft. So how does this all relate to boundary orientations? We would predict that boundary orientations would follow that where that precipitation is falling. And we see that our inflow-outflow angle is modifying our forward flank reflectivity gradient orientation in that first column, our forward flank convergence boundary orientation in the second column, the left flank convergence boundary orientation in the third column, and SVC orientation in the last column. So it's correlated with all of those, perhaps the best with the forward flank reflectivity gradient. But it is changing things. Now, if we measure where the updraft is and where the downdraft is, those centroids relative to each other, that angle, that actually predicts the orientation of the boundaries better than the inflow-outflow angle alone. So it really is where these cold pools are at, where the downdraft is at, where the cold pools are oriented relative to them. If we look at the inflow-low angle, the inflow-outflow angle does modify the inflow-low angle a fair amount with a 0.55 R squared value. And if we compare the boundary orientation to the inflow-low angle, we can actually see that they're moving in tandem to each other. So our original hypothesis that the downdrafts and the boundaries would be far away from the inflow-low is technically not correct. They are both moving together. If we look at the winds in the vicinity of each boundary to gauge kind of a streamwiseness, so we are modifying the winds with the inflow outflow angle. The top is kind of streaky because of the Kalman filter centering algorithm. But if we go to the middle and go back to the updraft downdraft angle, that is highly correlated with the winds. And so the winds are changing as well with the boundary orientation. And so if we kind of compare the boundary orientation at the bottom here to the wind direction around that boundary in the y-axis, we can see that with the upper level veering, the high inflow outflow angles, we have relatively boundary parallel flow in the vicinity of the forward flank reflectivity gradient. But as we have smaller inflow outflow angles, more upper level backing, we get more boundary opposed flow. We have our winds that are crossing that forward flank reflectivity gradient. This is relatively the same with the forward flank convergence boundary. However, all of this is boundary opposed flow. It's just the degree of opposition to that boundary. And that is actually preventing that density current from propagating further because we have more balance with the vertical wind profile. And then the left flank convergence boundary is a pretty weak correlation overall, but it is well within the boundary opposed flow regimes as well. So relating that back to SVCs, we already talked about that the inflow outflow angle does modify the SVC orientation, which has been shown to be important in the past. I'm not sure which way is the most important, but it is. Magnitude-wise, there really is no correlation whatsoever. So the inflow outflow angle does not affect boundary or SVC magnitude. However, if we again look at the population of presence versus not presence, the SVC is more likely to occur in upper level backing or small inflow outflow angles, which is an interesting idea as well. And this also is against my original hypothesis that I proposed. So that's pretty important. TOVs really no significance whatsoever with inflow outflow angle. So finally, low level shear. So we know that low level shear drives the mesocyclone strength. That vorticity from the environment goes straight into the updraft, rotates. And it also causes TLV formation. So our low level shear is highly correlated with our low level mesocyclone across the board in every metric we looked at. If we compare the low level shear magnitude to the inflow low magnitude, we actually see a stronger inflow low with larger low level shear as well. However, the distance, instead of increasing like it did with storm relative inflow, the distance of the centroid of the inflow low actually decreases, which means it's getting closer to the updraft. And this is physically caused by the nonlinear dynamic pressure perturbation in the mesocyclone extending into the inflow and actually pulling that inflow low a little bit closer. Our angle is slightly affected by the low level shear, but not a lot. However, the low level shear does affect that orientation of the updraft downdraft angle. So where the downdraft is relative to the updraft is actually more counterclockwise relative to the updraft for high low level shear environments. And we can see this a little bit with our outflow surges. Our centroid does rotate a little bit to the left from this vertical line here. And the magnitudes is strongest with low level shear. The most surges are occurring there. But the area does not meaningfully change between each experiment as well. So that centroid does shift though. And we can see with the small raindrops, we have a lot more small raindrops in weak low level shear environments where that precipitation is just falling down. Whereas if we have strong low level shear, we're actually getting some size sorting taking place in the low levels. And so we're going to shunt some of those small raindrops further to the north and west. And so we're getting a smaller concentration of small raindrops. Our cold pool, again, follows that directly. And in this case, that centroid is incredibly close to the updraft for low level shear. And we know that cold rear flank downdrafts are bad for tornadoes. And so that also is correlated where not only do we have less environmental vorticity to actually create the tornado, but we have stronger cold pools as well that could hinder tornado development. Whereas with higher low level shears, we're getting that centroid a little bit further away and a little bit warmer to overall support the storm dynamics. So if we go forward to orientation of the boundaries, there is a weak correlation, very weak. The forward flank reflectivity gradient is like 7% of the variance explained by the shear magnitude. But if we go forward to the forward flank boundary and left flank boundary, that's closer to about 15% of the variance explained by the low level shear. So again, moving that cold pool, we can see that is affecting the boundary orientation a bit, as well as the winds on the bottom there in the vicinity of the boundary. So let's bring that back in. How does that affect SVCs? The SVC magnitude is strongly impacted by large low-level shear. So we have more environmental shear. We expect there to be stronger streamwise vorticity within the SVC. And then we're building upon that even further by horizontal stretching as well in the inflow low due to the stronger mesocyclone. So we'd expect there to be a strong correlation there, and there is. Orientation, not so much. Interestingly, however, if we look at the presence of the SVC, it is most likely to occur in moderate low-level shear environments, not strong low-level shear environments like hypothesized. So that's intriguing. Now, obviously, this is a trifurcated distribution, but you can just see from the distribution statistically, the numbers don't quite add up, but it is predominantly in that center there. And our low-level shear is highly correlated with TLVs on the bottom there, and the most TLVs occur with larger low-level shear. So again, that physical mechanism checks out. So that kind of gives us more credence to trusting kind of the SVC outcomes here. And just to wrap this up, I wanted to improve the inflow-outflow angle. This was kind of developed a while ago for just general balance between inflow and outflow. But with this data set and the boundary orientations, I can actually improve upon this. So statistically, testing each shear vector with every other shear vector, I found that the best correlations occurred for the forward flank reflectivity gradient at the layer between about 1,500 meters to 11.5 kilometers with a really high R-squared value of like 92%. The slope is near unity, so it's a near one-to-one comparison, just with about a 4-degree bias. If we look at forward flank boundary, there's a little bit more variance here, but again, we have a pretty strong signal here from the lowest levels, 100 meters, to about 10.3 kilometers. The left flank convergence boundary is a lot more variance. Still a meaningful R-squared value, but the predictive quality of that would be considerably less because of other internal storm dynamics controlling that. So moving on to the downstream impacts here. So if we compare all of our TLV's presence to all of our SVC's presence, the TLVs are in yellow, the SVCs are in blue, and the overlap of the Venn diagrams is where they are occurring simultaneously. If we look at our total data set on the bottom left, we can see that only about 30% of the TLVs are occurring with SVCs, and only 38% of the SVCs are occurring with TLVs. So not a really clear smoking gun signal, as we would expect. And looking at individual experiments, we don't see a whole lot of trends either. We see some interesting features, but we're really looking for a smoking gun of tornado depending on the SVC. So where the yellow overlaps with the blue the most. And we actually see that in the low-level shear, the medium low-level shear environments. That is the only experiment where more than 50%, is 60.7% in this case, of TLVs occur with SVCs. And there are a lot more SVCs in general, but there's more TLVs that are associated with that. For a weak low-level shear, there's very little SVCs and TLVs, but there still are some. And for a large low-level shear, we have a lot of TLVs in general, and a lot of those SVCs are associated with TLVs. But that doesn't necessarily mean that all of the TLVs are caused by the SVC. The storm could just produce the TLVs without the SVC as well, due to the high low-level shear. But for the medium, that may indicate that there is some tipping point of the updraft that couldn't quite produce a tornado, but with an SVC present, it is able to. And so that's why we see that signal potentially. So I released a bunch of parcels in the forward flank of each of a couple supercells, and I wanted to analyze, and I released them every 5 minutes. Accounting for the advection speed, we should have continuous flow of parcels through the entire experiment, and then see where those parcels end up. So This is one example that I'm going to walk through. I don't have a lot of time to show all of you 22 experiments, but this is one of the most prolific SVC cases that I identified, long lasting and strong. In the top right or top left here, we can see the supercell. There's a lot going on here, but the SVC is basically in this yellow stippled region, and we're doing a vertical cross section through that. And if we look at streamwise vorticity in that cross section, we see a perfectly nice rotor extending about 1.25 kilometer up. And there are multiple actual spirals into that. And so this is a very mature, developed SVC. And this is right after tornadogenesis in this case. If we look at the streamwise vorticity in the parcel view, we can see a very similar feature as we would expect. And that's where the time is plus or minus 30 seconds from this 215-minute time period where parcels are moving through that plane. So this is an instantaneous snapshot of the parcels moving through that plane. So we see good streamwise vorticity. If we look at the tendencies, again, we see a lot of tilting and stretching, but there's an interesting dichotomy of diagonals where the upper left to lower right is a positive stretching and tilting, and the upper right to lower left is a negative stretching and tilting. Regardless, though, these magnitudes are much stronger than, say, the baroclinic vorticity tendency, which is much weaker, and the positive is located on the leading edge of that cold pool, as we would expect, and as well as at this trailing leading edge of the cold pool. And there are also negative regions of baroclinic vorticity generation as well. And then subgrid scale mixing and implicit diffusion have some signal, but they're relatively weak in comparison to the tilting and stretching. So we again confirmed what I found in my master's work, and others have found as well. So let's look at where these parcels actually end up then. So this is a kind of a complicated plot. The upper left is the supercell, cold pool in blue, reflectivity in gray. We have our parcel paths in yellow as they're flowing into the low level updraft. And at 1.5 kilometers, which is used instead of 1 kilometers because the SVC is still at 1 kilometer, so you have appreciable vertical velocity there. So for my low level updraft, I looked at 1.5 kilometers, and we see where the parcels end up that are non-SVC parcels in yellow, and the SVC parcels will show up in black. This first black cross section here is this first cross section down here. The blue cross section, second one is the second one, and then teal is the bottom. And these cross sections are time lagged according to the advection correction. So the parcels time as they pass through that cross section is the analysis period. So that doesn't necessarily correlate to that top analysis, if that makes sense. So if we play this out, we can see that the storm is slowly evolving and maturing. Our low-level updraft is strengthening, and we get our SVC occurring. And a lot of instantaneously, a lot of our SVC parcels in black are ending up in this upper left region of the low-level updraft, and then kind of around the backside in this occlusion updraft overall as well. Pretty much none at all end up in this leading comma shield part of the low level updraft. All of them are shunted in the back. And honestly, you can see in the streamwise vorticity in the purple here that you can just take that SVC and just tilt it in the vertical, and it still retains almost the same shape with relatively little deformation. And if I go forward a little bit further, we can see a really strong manifestation of that with the spirals. Oh, dang it. If I move forward about here, we can see that those inner spirals are almost perfectly posed onto that horizontal cross section at 1.5 kilometers. So that SVC is just tilting right up. And if we move forward a little bit, this is around tornadogenesis time right here. And we actually see the beginnings of the TLV in this fuchsia color at the surface. And the SVC parcels are almost predominantly directly above that, where the strongest updraft is as well. There is a little bit of non-SVC parcels, but if we look at the cross sections, some of these non-SVC parcels are from the left flank boundary. So north of the SVC flowing in, and those are flowing at a very low level, and then getting directly tilted up and into that low level updraft as well. And that is the airstream where the vortex patch is coming from, where that TLV is forming at. And so we get a mix of SVC parcels above and then the TLV parcels pretty much from below. And then moving forward, that updraft fully occludes back, the storm cycles, and then we get a new updraft forming to the east. And again, we have our SVC predominantly feeding that northern part of the low level updraft. So I wanted to look at how the SVC portion of the low level updraft compares to the entire low level updraft. So on the top here, we have at each threshold of vertical velocity, starting with 5 meters a second. As we increase our threshold, our low level updraft area decreases in size. And so that's seen in the colors here, where the warmer colors are smaller size, but we have higher velocities overall as time progresses. And so our updraft is strengthening with time before tornadogenesis. Our updraft width at the lowest threshold at 5 meters a second kind of maximizes at around 180 minutes. And then kind of wanes a little bit. So the updraft width, low level updraft width isn't super correlated necessarily, but the updraft strength is pretty monotonically increasing with time towards the TOV genesis. Now, if we take where there are 3 SVC parcels within each grid point and mask that out and take that area compared to the entire low level updraft area at, say, each threshold, we can kind of compare the ratio of how much the SVC is contributing to the low level updraft at each vertical threshold. And below about 15 meters a second, the SVC is contributing about 20 to 30% of the low level updraft there. So a lot of those non-SVC parcels are contributing to that shield portion of the low level updraft and not to that comma head. However, originally with time, there was no organized comma head necessarily, and the SVC wasn't fully strengthened. However, at about 170 minutes, we get this kind of regime change where we switch from the strongest parts of the updraft not being affected by the SVC to being completely affected by the SVC. So nearly 100% in the warmer colors there, nearly 100% of the fastest vertical velocities in the low level updraft are where the SVC is tilting up. And that implies that there's stronger vertical accelerations below that, which could lead to, say, tornadogenesis and vortex stretching. So that implies that there is a really strong importance of the SVC to this low-level updraft and low-level mesocyclone overall. If we kind of take a 3D look at things, I showed this at SLS. There's a lot going on here. Blue is the identified SVC region. Yellow is lambda 2, which is kind of can be thought of as like a vortex tube of sorts where rotation is dominating, but in full 3 dimensions instead of the Akubo-Weiss, which is only in 2 dimensions. We have our vertical accelerations in the red, which is again right below where that stream tubes are at. And then our vertical velocity of the updraft in gray is 10 all the way up to black in 30 meters a second. So we can see this left flank boundary is oriented right underneath the SVC. And this lambda 2 tube is along the leading edge gust density current of the left flank boundary. And as it approaches the SVC, it gets tilted up and just completes all the way up into the updraft, connects there. This is a tornadogenesis failure. It tried, but it kind of blew itself apart with time. And so, but the left flank boundary still kind of stays relatively there. It comes and goes. But with time, we can see that there is lambda 2 in the center of that SVC core where we get a strong rotor developing and rotation is dominating. We also get a continuous region of vertical accelerations, nonlinear dynamic accelerations below where the SVC is tilting up. And if we run this forward in time as well, we can see that the updraft actually begins to descend where that SVC is tilted up. And so those accelerations over time are increasing our updraft at that point. And moving just a few minutes further, we get our first tornadogenesis in that region. It's really hard to see here, but that's the pink in that region there. And so that vertical acceleration finally was able to stretch a favorable position vortex patch there, leading to tornadogenesis. And then it will slowly dissipate with time. But we do get that there's leading edge vortices along the SVC, kind of like that vertical vortex sheet wrapping up due to horizontal shearing instability. But these vortices are actually wrapped around the rotor and are entrained into the rotor leading into the updraft. And there's one right here, and then a second one kind of right here as well. And the second one actually forms the second tornado. And so we see at the rear flank gust front interface that accumulation of vorticity from that vertical vortex sheet is just kind of sitting there and is in a favorable position to be stretched into an updraft. So the SVC has two different kind of tornado genesis mechanisms in this simulation, from the vertical accelerations, stretching pre-existing baroclinically driven vertical vorticity from the cold pool versus the vertical vortex sheet on the leading edge of that. If we analyze the VPPGFs of the SVC just more in depth, we really just want to hammer this down. So we'll take cross sections down the axis of the SVC. The top row is that black cross section, which is north of the SVC, which is hard to see, but kind of in this pink red region right here. The blue cross section is right through the middle of it, which is this middle cross section here. And then the green cross section is the bottom here, south of the SVC. In the brown to yellow contours, we can see our vertical PP pressure gradient force, our vertical accelerations caused by the SVC vorticity itself, the nonlinear dynamic component of that. And we can see the streamwise vorticity magnitude in the purple there. And so even across the entire axis of the SVC in this middle panel, we do have some vertical accelerations towards the center of that SVC. But as we approach the updraft and the SVC tilts up, we have a maximum of vertical accelerations there. Prior to tornado genesis, this is on the left is 3 minutes prior to tornado genesis. The middle is at tornado genesis, and the right is 3 minutes after tornado genesis. So the vertical accelerations are locked in there through that entire time. And so we're really just waiting on a favorable vortex patch to get in there. And I approximated the location of the vertical vortex patch there, which is located nearly identical where that strongest VPPGFs are located. During tornado genesis, the tornado shifts a little bit away from that as it kind of oscillates and forms, but then it snaps right back to that location 3 minutes after and sits there, as that's where the most favorable place to maintain that tornado is at, where that strongest acceleration is at. So finally, I wanted to look at kind of this chicken and egg problem. So does the streamwise vorticity in the SVC drive the low-level mesocyclone? Or does a low-level mesocyclone strengthen the SVC due to the horizontal accelerations through the SVC? So I took a stab at this. This is kind of preliminary, but the blue line is our low-level mesocyclone strength. And in this case, I used vertical helicity at 1.5 kilometers. I took a cross-section upstream of the updraft where the SVC was at by about like 7 kilometers or so. And I identified the SVC, calculated circulation around that to estimate the strength of the SVC at that region. And in the orange line, we can see the circulation with time as well, instantaneously. So that's well correlated with our low-level updraft. And we can see that the peak here is relatively close to the peak in low-level mesocyclone, but about 3 minutes afterwards. Again, there's another peak right here, well correlated with this peak. And then there's a dip, well correlated with this dip. So there seems to be some signal there where the low-level updraft and the SVC magnitude increase hand in hand, or maybe the SVC increases a little bit later. But, so that's been seen before and presented before. However, that SVC air is still 7 minutes, 8 minutes upstream of the low-level mesocyclone. So by the time that air reaches the updraft is due to the advective timescale 8 minutes later. And so we actually see a significant lag. So when comparing our observations of SVCs with the Ka radars, that data is a good 5 to 8 minutes ahead of where that actually is reaching the updraft. And so there does seem to be that the mesocyclone strength is driving the SVC magnitude and not the streamwise vorticity within the SVC driving the mesocyclone strength. I don't have time for this second case, but I ran similar analysis and found very similar things. I wanted to talk about low-level updraft real quick. Kofor et al. Talked about these comma-shaped low-level updrafts. I did a similar analysis with mine and found that the strongest vertical velocities were in this comma head and occlusion updraft of my low-level updrafts. And most of my low-level updrafts looked like a comma for most of the time. The non-traumatic ones with weak low-level shear kind of had a very elongated, large comma shield, whereas the comma heads were where the strongest streamwise vorticity and the strongest vertical velocities were located at. So that kind of confirms that hypothesis as well. So wrapping this all up, going back to our upstream things, if you remember that from the very beginning, our storm relative inflow did increase the likelihood of an SVC, but did not increase the strength of an SVC. Our physical pathways were correct that we identified, but something was missing there between our actual cold pool formation and inflow low formation and the SVC magnitude as well. Going to our upper level backing versus veering, that was proven wrong. Our upper level backing of winds actually favor our SVC development, and there is really no correlation with strength whatsoever. The inflow low moved with the boundary orientation, so they moved in tandem relative to each other. And the vorticity did have a larger crosswise component, but kind of going back to these parcels, forgot to mention this here. There's two kind of primary airstreams here. There's a long axis SVC airstream, and then there's this environmental airstream that is starting not along the SVC axis, but gets entrained, moves up over the rotor and gets entrained into it. And through that takes a large left bend in the airstream, which is associated with river bend effect, converting crosswise vorticity to streamwise vorticity. We're also converging all of that vorticity, environmental vorticity out there into a single region closer to the updraft. And so that will also likely lead to stronger tilting and stretching of vorticity as well. Let's see here. So for low level shear, that did not explain the existence. The SVCs were predominantly occurring in moderate low level shear, not strong low level shear, but it did drive the strength as well. And again, our physical pathways were correct. Stronger mesocyclone led to a stronger inflow low, greater accelerations. But the existence was a little weird. I looked into that a little bit more. And what I found was that with stronger storm relative inflow, our cold pools were a lot stronger, but further away. And so we had kind of a larger, broad forward flank precipitation and density gradient. And so we didn't actually have strong density currents like we did for the other simulations. And then when they did occur, there was so much vorticity already within the SVC that it actually blew itself apart. It shredded itself with time. And so it didn't last for the 2 hours of our longest SVCs. They lasted a lot shorter time period. And that the shredding of the SVC ended up into small little vortices of random sign. And so that was not a coherent tube of streamlined vorticity that could affect the low-level mesocyclone as much. The downstream effects, the SVC was not a smoking gun for TLVs as we expected. The likelihood is better with an SVC present, but only for moderate low-level shear cases, probably. For high low-level shear cases, it probably doesn't matter. It was going to produce a tornado anyway. And for low-level shear cases, the SVC was just not strong enough to support the stronger low-level updraft to stretch the anti-vortex patches that were there. And so it's only important for moderate low-level shear. The environmental parcels end up on the shield of the low-level updraft, whereas the SVC parcels end up kind of in that comma head. So I kind of made this diagram to show this a little bit. This is kind of stepping through at 250 meters. If we increase in height, we can see the shaded region is where those SVC parcels at, whereas the white region is not. And stepping up to 1.5 kilometers, we get above the SVC here, minimal influence, but we get this kind of wrapped comma shape with the maximum SVC parcels and vertical velocity vertically stacked with the tornado, which is what we want for tornado maintenance and has been shown in the past. And as we increase in height, we just kind of get that continuation vertical stack, and the SVCs parcels are within the kind of the strongest vertical velocities, and potentially shift a little bit to the northwest of where I have it there, but relatively in that same position. And then finally, I think I definitively showed that there is strong vertical accelerations underneath the stretching of the, or tilting of the SVC that are driving tornadogenesis in numerous cases. I only was able to show one, but this is occurring in other simulations as well. Now, this is not, again, the smoking gun. There are plenty of other mechanisms for TLV genesis, but this does seem to be one of them. And so hopefully that will kind of enlighten operations, as well as provide a little bit more clarity on what to look for in the field and how important SVC actually is. With that, I will take any questions.
Made it.
Made it.
Perfect job. All right. I forgot to mention this at the outset. If anybody online has questions for Alex, please do feel free to chat them, or I'll try to look for a raised hand here, perhaps. In the meantime, I'll be glad to take questions from the audience that's present here. I'll flip the. Well, you guys can all see. See there. Good enough. Yeah.
I guess I'll go ahead and get started. So something that you mentioned to me a while ago that has been sort of sitting in the back of my mind is the idea that storms and their structure and dynamics are impacted by TLV genesis in the first place, right? And that there's a sort of memory that exists. Maybe memory is the wrong word, but there are downstream impacts in time to having that first tornado genesis that occurs. Did you happen to do any analysis, or sort of maybe even just at a cursory glance see any change in the relationship between the SVC and all the many dimensions of impact that you looked at pre and post that first TLV, if that did happen?
Yeah. So the question was, is there any memory associated with the simulation, and how does the SVC kind of impact that and stuff a little bit? So what you didn't see was my hundreds of failed simulations that I ran that had surging cold pools that immediately went out and the storm just died. That had immediate tornadoes, and that changed the entire evolution of the supercell, cold pool generation, SVC generation, and stuff. And those are barotropically generated tornadoes, and that's a common thing using updraft nudging initiation mechanisms. And there's been work to better that. I haven't done any specific analysis. However, I did notice that even with these simulations, there is that initial kind of cold pool development and surge outward from that density current. And with time, that pretty much washes away. However, there is still a kinematic memory of that density current there. And that is a location for increased convergence later on. And in actually some of my strong storm relative inflow simulations, even though this is a free slip bottom boundary condition, no induced turbulence whatsoever, I get these almost horizontal convective rolls and instabilities releasing in the inflow. And they often occur on that original density current that we long forgot about. But that little kinematic signature kind of grew with time and kind of created this turbulence and stuff. So that was interesting. I didn't look a whole lot into that. But it is definitely something that should be looked into, and the memory of how this affects. I mean, even just the updraft strength initially, your updraft mechanism will have long-lasting impacts on whether you even produce an SVC or not, regardless of the environmental conditions that I just showed do drive that the vertical wind profiles. And so how stochastic that is, I mean, kind of the tornadogenesis problem too. It's so stochastic that we can try to relate that to environmental parameters, but it's really difficult.
map up there.
Yeah.
You might want to tackle that one.
All right. So really great work, Alex, from our awkward early days at the Texas Weather Conference to here. I have a slightly self-serving question, but can you speak to the relative importance of the SVC modulating boundary opposed winds and associated inflow-outflow geometry, increasing the residence time of near-surface rotation beneath a low-level meso versus the strength of the meso itself? No, that's a good question. Let's see. So when you have more boundary opposing winds, yeah, so you have more crosswise vorticity pretty much going into that SVC, and the vorticity within the SVC is not necessarily streamwise, but it actually does turn the winds, like I said, and how that relates to our tornadogenesis and stuff. Going back to your paper, I'd have to revisit that and stuff, but the it's a good question. I would have to look at that more. There is some dependence on where that low level updraft is relative to the vortex. And in some of my upper level backing environments, I'm not changing the low level wind, obviously, I'm changing the upper level winds there. But that boundary orientation, you actually get a really elongated updraft along that strong density current there, instead of more of a compact, tight, like circular low level updraft that I kind of showed in Finley's study as well. So it definitely does have an impact on where that updraft location is and where it's most concentrated at, with respect to the tornado vortex.
Questions from inside the room here? I might have another one. Yeah, I'll let you.
Checking Zoom.
Oh, you got. I'm sorry.
Go for it. Julia coming in with a stinger right there. So does free slip versus semi slip matter? Yes. It would have a significant impact, and talked to multiple people about this. Zhang and Dawson had a paper that looked at the boundary orientation relative to the updraft and how that changed between free slip and semi slip, and it was significant. And that really breaks my inflow outflow angle kind of analysis based on the statistics and predicting that with the vertical wind profile. That is very highly dependent on this simulation setup. I'd like to kind of expand that to more real life cases, but you're right. Having semi-slip would affect the boundary orientation, which can have obviously an impact on SVC orientation and put it into a less favorable or more favorable environment. The semi-slip will also affect vorticity generation, and a lot of those. So I talked about the left flank convergence boundary parcels ending up into that low level updraft in that case that I looked at. And those parcels are originating very close to the ground. And so that would have a lot more vorticity possibly there to lead to possibly a stronger tornadogenesis mechanism, but it will also change everything else. And even the turbulence could kind of throw the SVC balance off. And from what I've seen from a couple of the papers out there, you don't get as clean or dominant SVC from a semi-slip simulation, but we see them in nature. So there's something still to be done about improving the quality of semi-slip and turbulent bottom boundary conditions, that they're both wrong, but for different reasons, semi-slip versus free slip. And so since this seems to be producing more close to what we actually observe, I opted to go with the free slip. So good question. I think that answers Fayaz's question as well. Let's see. Anybody else or online?
Going once. Ah,
From outside the field, I have a question. So besides like hypothesis testing and linear regression, I think that other methods for experiencing like barrier analysis, like analysis or types of machine learning techniques or perhaps the triple value or the friends who less probably a failure with mistakes and also look at how system react based on parallel with series and sort of the interaction and how to characterize importance factor contributing.
Yeah. Yeah, so to repeat the question for the online folks, basically have I looked at different analysis on the upstream side of things, using like principal component analysis or multilinear regression or other methods to kind of figure out what's going on here, and sort of. So in my previous early PhD work, I looked at some of those tools to identify the SVC primarily. That is a really, really tough cookie to do. And it kind of is a natural extension of identifying vortices in just normal fluid dynamics CFD simulations. It's really difficult. And so I opted to do like a lambda 2 method and do a lot of complicated algorithm to develop that. But I looked at principal component analysis to kind of identify the SVC better. I did look at multilinear regression a little bit for the kind of the optimal shear vectors for figuring out the boundary orientations relative to the shear vectors and stuff like that. Machine learning I never touched, but that I wrote in my dissertation that is a low-hanging fruit for SVC identification, as well as relating the SVC to the tornado statistically that just a linear regression is not able to do, or my Venn diagrams or whatever. And so that definitely is the next step that could be done by someone that to look at a better relationship there. So yeah, that was a great question. Yeah, absolutely. And I even with the parcels, I identified the location of the parcel based on my SVC identified algorithm. But I wanted to classify like a clustering algorithm to figure out the different airstreams and where they're going and how they're behaving, and then cluster them with like vorticity tendencies and show this is the region of the strongest baroclinic tendency. Where does that end up versus stretching versus tilting versus whatever? And so that's definitely something that I wanted to do, but wasn't able to, didn't have time. Yeah.
Anything else?
Doesn't look like it, no.
All right, going once. Going twice. Oh.